So Steve Cooley is going to go over this finite burn tutorial. So instead of doing impulsive burns, he's going to show you, demonstrate to you how we can do finite burns in GMAT. And yep, this is it. So this is going to be on page 70, I believe. 70 out of 681 in the user's GMAT user's guide.
How did you circle with them?
Oh, that's right. Let me show you that.
Yeah.
Okay. So we have the instructions actually here.
Okay.
So zoom in is actually Control 1. Just zooms in, and you can just pan with that mouse if you need to, and just hit Escape to just come out.
Okay.
And draw is actually if you just zoom in first and just click on the mouse, we just begin to draw.
And I have to click first. Okay.
Yeah, exactly. Yeah, and then you can just do.
Okay.
So this Escape will actually undo the drawing also, and the zoom in, zoom out.
All right, so
you can try it again. Yeah.
So let's go back to the beginning. Okay. And then.
Let me know if you have any issues.
And where's the GMAT?
Actually, scroll here. This is the one that.
One on the far right.
Yeah, on the right. Yeah.
And it's a fresh case. Okay.
Yeah, so you can just insert and.
Perfect.
Let me actually pass out the.
Oh, okay.
We actually have tutorials.
Oh, okay.
To make it easier for them.
Oh, perfect. How come you lose source?
Oh, actually, you just gotta
hit
press this guy every now and then.
Okay.
To bring it back to life.
Okay. So
this is the. How do you find it? The finite burn tutorial for today's Apogee.
So like Rizwan said, I'm going to do finite burns. You know, up to now you've just done impulsive burns. You kind of assume that you applied a delta V instantaneously, and your velocity changed, you know, in an instant. If you actually want to fly a mission, you have to simulate a finite burn, and you have to actually apply the thrust, and you have to simulate a thruster and a fuel tank, etc. So that's what I'm going to talk about. So this case is we're going to do a finite burn to raise apogee, and we know from orbital mechanics that the most efficient place to do an apogee raising burn is at perigee. So you'll see when we actually put together the sequence, I'm going to propagate GMAT to perigee, apply a finite burn maneuver, and you propagate half an orbit to apogee, and you should be at a desired apogee radius. For this case, we're going to use 12,000 kilometers. So what are we going to do here? We're going to create and configure the spacecraft hardware and finite burn resources that you need for a finite burn. We're going to create a mathematical object called a differential corrector. Rizwan, did you talk about the differential corrector a little bit before? Or
Joel did. What do you
Joel?
You can just refresh.
Okay, so differential corrector is a mathematical object. You have control variables that you vary, and then the goal is to achieve a certain parameter. And so it's based on Taylor series approximation using, you know, multi-dimensional derivative. It's pretty straightforward. But you have to create that mathematical object in GMAT first. And then we have to create a target control variable. This is the thing that we're going to vary. For us, we're going to vary burn duration because it's a finite burn. You know, you might start out with a certain guess for how long it's going to take in seconds, but that's what you actually want to solve for. So we're going to create that variable called burn duration. Then you need to create your finite burn, and that's done with a begin finite burn command and an end finite burn command. And I'm going to go explain this all in great detail. And then you need to create what's called a target sequence. That's where you embed the differential corrector that you created to achieve your goal. So GMAT, you kind of can think of it, you have to assemble things in pieces. It's like a car. You have a wheels, you have an engine, you have a transmission. You create those first, and then you put it all together. So what we're going to do now is we're just going to create various objects. It's kind of an object-oriented way of thinking about things. And then we'll paste them all together, and then we'll create our mission sequence and go. So now let's create so we're on page 2 of the tutorial. So now we'll create, configure our spacecraft hardware and our finite burn. So I'm just going to do everything from scratch. Feel free to ask questions. The default GMAT script comes up with a spacecraft called default spacecraft, so that's fine. If you double click, you see it comes up with a default. Comes up with a default orbit, low Earth orbit, and we're not going to change anything here. We'll use that, but we do want to create some hardware. We want to create. So go to Hardware, Add a fuel tank, add a thruster. So we've created these abstract objects, and in GMAT you just double click things to bring up more information that you can edit. So for the fuel tank, it has default masses. You see that it's pressure regulated. The other option is blowdown. Pressure regulated means just the tank is kept at a constant pressure. Maybe there's a nitrogen tank up there or something, but whatever it is, they keep it at constant pressure. The other option is a blowdown tank where the pressure decreases as you use the fuel. We're just going to use the default pressure regulated. And then now double click on the thruster object and it brings up this. So some things to notice. We're going to model fuel use. So we want to hit this little button here to decrement the mass. We're going to allow fuel to be used. So when you fly a real mission, you want to know how much fuel you use. So you have to go ahead and decrement that. And then select the tank that we just created right there. And when you have the thruster object, it comes up with the default coordinate system. And here it's the Earth-based VNB, which is velocity normal binormal. So the x-axis is along the velocity vector of the spacecraft with respect to the Earth. The n is the orbit norm. The y-axis n is the orbit normal, and b is the binormal, and that completes the triad. So you see here by default, the thrust vector is 1, 0, 0. That means all the thrust is going to be applied in the x or v direction. So that's what you want to do if you want to raise your apogee. You want to apply your thrust in the velocity direction of your spacecraft with respect to your central body, in this case, the Earth. So the way GMAT models the thrust is pretty common in the industry. The thrust for a chemical tank, the thrust is a function of the pressure in the tank and the ISP of the fuel used. So, and that's modeled with various coefficients here. So you can edit the thruster coefficients here, and C1 is just the linear term. So that means it's a constant with thrust of 10 newtons. These other terms have to do with pressure and temperature in the tank, but we're not gonna have any pressure dependence. We're just gonna use constant thrust. But the one thing I want to do is change the value of C1 to make it a bigger thrusters, so it doesn't take forever to do this particular case. This might be an unusual value for the thrust, but just for this purposes of a test run, it's fine. So I'm going to make this 1,000 newtons. So it's a pretty big thruster. So again, constant thrust of 1,000 newtons, no dependence on pressure or temperature of the tank. And then click OK. You could also edit the coefficients for the ISP, which is a measure of how efficient your fuel is. Higher is better, but we're not going to mess with that. No, if you had like low thrust xenon or something, this would be 10,000 or something like that. But this is a somewhat typical value. I've seen 220 as a typical value too for this. Okay. We hit apply. And then I occasionally just save my stuff so if it crashes, I don't have to retype things in. Okay, so now we've created the tank and the thruster. Kind of like a car, if you create a wheel or an engine, you have to attach it to the spacecraft. So that's what we're going to do next. We're going to go up here to the default spacecraft and attach the tank and the thruster to the spacecraft. So under tanks, bring fuel tank over to the selected tank area, hit apply. Go over to actuators, bring the thruster over to the right-hand side with the arrow, hit apply. So now you've applied attached thruster 1 to the spacecraft and fuel tank 1 to the spacecraft, and we've already associated fuel tank 1 with thruster 1. So that means when you fire thruster 1, it's going to take fuel from the tank. So we'll need a single finite burn for this tutorial, so we'll go ahead and create that. You get a default impulsive burn, but the finite burns don't come as default, so you have to create one. So right-click under burns, add finite burn, double-click it. You have to, when you define a finite burn, you have to say what thruster set you're going to use. Well, we're going to use the one that we just created, thruster 1. Hit apply. Now we're going to create a differential corrector. Go under solvers, boundary value solvers, and we're going to add a differential corrector. And then double click on it. And the differential corrector, you have to, when you use the differential corrector, you have to calculate a derivative. You have to calculate a derivative by finite differencing. And there's different methods you can use for that. You can do forward difference, central difference, backward difference. Different algorithms you can use. The default here is fine. Maximum iterations is how many times it's going to try to find your solution. 25 is fine. So everything here is perfect. You usually don't have to mess with this so much. If you had a really sensitive problem like a libration point mission or something, and you wanted a little bit accuracy from your derivative, you might go with the central difference here. Because then it calculates two derivatives, a little bit before the time and a little bit after the time. Okay, now we're going to create a control variable. And to do that, you go to the variables area here, right-click. And you can call this anything you want, but you might as well make it easy for yourself and call it, have intuitive name. So this is for the burn duration. And this is a control variable. And this is the thing that we're going to allow the targeter later on when we create it to vary. And we want to find out how long do we have to burn so that when we do a burn at perigee, we get to the apogee of 12,000 kilometers, a half an orbit later that we want. So you need to give it a default value. I'm going to give it a value of, I don't know, 20, but we're going to overwrite that later anyway. But in general, it's good to know that when you create a targeter, you have to give it an initial guess. And an initial guess of 0 is bad for numerical reasons. So just pick a number that's in the ballpark. I don't know, 200 seconds. And then click the arrow and close. Okay, so now we've created all our resources with this first tab. Now we go over one to the next tab, the mission tab. This is where you actually start doing things and putting together everything that you've created on the other resources tab. And it's good practice to name your segments something meaningful to you. Right now, it might not make a difference, but when you come back and look at it 6 months later, it's good to have physically significant names here. So I mentioned earlier that we want to propagate to perigee because we know from orbital mechanics that a good place, the best place, the most efficient place to perform a maneuver to raise apogee is at perigee. So you do a burn at perigee, then you propagate for half an orbit to orbit apogee. So we're going to name this prop to perigee. But just because we name it that doesn't mean it's so. We have to double click it and bring up the properties and make sure that's what we're going to do. So change it to apoapsis, and you'll see the default is Earth. Hit OK. Apply. Okay, now we create a target sequence. And remember, the target sequence is the thing that has your direct differential corrector embedded in it and has the thing that you're going to vary and the thing you're going to achieve. So insert before a target sequence. And so we're already at perigee, so the next thing that we're going to do is perform a burn. Okay. So I forgot to mention that you can also rename your target sequence to anything you want as well. And I'm just going to call it raise apogee. Okay, so at this point, I'm just going to create a whole bunch of objects and insert them into the mission summary here, into the target sequence. I'm just going to create them and name them, and then later on, I'm going to double click on each one of them in turn and fill in its various properties. So this is just putting together the shell or the skeleton of what we want to do. Yeah, sure.
A couple of things. I think you were propagating to apoapsis, but I think this sheet was having us propagate to periapsis.
You're exactly right.
And I also think you might have an order issue that you want to propagate first and then.
I sure do.
Okay.
Thank you.
Thanks.
Yep. I don't think GMAT has the feature to like, some of our competitors. You can take you could take the thing and move it.
Yeah, you'll have to delete it and then insert before.
Yeah.
You just have to insert before.
Yeah, insert before.
It's a feature request for folks that they want.
Yeah.
Or if you were in script mode, you can just copy and paste the right.
Yeah. Thank you for catching that. Right now, we start out the sequence by propagating to perigee. Later on, we're going to propagate to apogee. But we start at the periapsis. So now we apply our burn, and we're going to use it as a control variable. So the way you do that is with the vary command. And we'll define the control variable later. But just know to begin your differential corrector scheme where you vary the burn duration to achieve something, you started out with the vary. These are the things that you allow the differential corrector to vary. And in our case, it's going to be the burn duration, but more on that later. All right, so now you've created the control variables, or we will, coming up. Next thing you need to do is apply the thrust. So you have to basically turn the thrusters on. So the command to do that is begin finite burn. So insert the begin finite burn command. And again, the begin finite burn, really all it does is turn the thruster on. And then you have to turn the thruster on for a specified duration, and the way you do that is just insert a propagate command here. So insert before propagate. And then you want to turn the thrusters off, so that's an end finite burn command. So then you applied the burn. What do you want to do? Just propagate naturally to apogee. So that's another propagate command. Now you throw in the other piece to your differential corrector. You've already put in the vary command, but you have to tell it what you want to achieve. And now you put in the achieve command. And what do we want to achieve? Apogee radius of 12,000. And again, we haven't made it correct yet. We've just named things the way we want. So now we have a skeleton of what we want the script to do. And as I mentioned, now we'll just kind of go through each of the segments and make sure it does what we want it to do. So we'll start with, we already fixed the perigee. It's going to propagate to Earth periapsis, so that's okay. Vary burn duration. So it uses the differential corrector that we created before. And we want it to vary the burn duration. So you go here and you go into the variable that we created, burn duration, and you choose that. So it's going to change the value of that variable. So that's really all it does. And later on, we'll use that variable. And what initial value do you want to use for the burn duration? Well, let's just pick. Again, don't use 0. We'll pick 200 seconds. And the perturbation is used to calculate the derivative. It'll try a burn of 200 seconds and then another burn of 200 plus 0.0001 seconds to calculate the derivative. So that's okay. And for different problems, it's very sensitive to the value of that perturbation. But for this kind of problem, low Earth orbit, it's pretty standard. You can just use the default. And the lower is the lower value that will allow the burn duration to be, will allow it to go to 0, but it's not going to go there. We need to pick an upper value. Well, this upper value of 3 is left over from an angle default, so that's not going to work. So well, we know it's probably not going to be more than 10,000 seconds. So put that in here. And the max step is, remember I said there's 25 iterations. For the max step is how much the differential corrector is going to allow the control variable to vary each iteration. So 0.2 is too small, because it only changes the burn duration by 0.2. So let's allow it to take bigger steps. Say 100 seconds. So that means if your initial guess is 200 seconds, the next iteration, the range is going to be somewhere between 100 and 300 seconds. It's kind of a way to force things to be linear if you just make things take small steps. So I think this looks pretty good. Start with 200 seconds. Perturbation is reasonable. Lower is 0. Upper is 10,000. Max step is 100. So apply. Turn the thruster on. That looks okay. It uses the default finite burn object that we created. And I'm going to rename this something a little bit better. Propagate for burn duration. Double click on it. So right now, the default says it's going to prop for 12,000. It's going to propagate for 12,000 seconds. So because it's sandwiched in between a begin finite burn and an end finite burn, that means it's going to burn for 12,000 seconds, which is not what we want. We want it to burn for burn duration number of seconds, that variable that we created. So let's go in there and change the object type to variable and bring burn duration over there. Okay. All right. That's pretty good. Then we have the end finite burn. And again, it's just going to turn off that finite burn object that we already created. Now we're going to prop to apogee. And so we change that. Now we tell it what we want to achieve with our differential corrector. So we're at apogee already by the previous command, and we wanted the apogee value to be 12,000 kilometers. And when you define the differential corrector, you have to say how close do you get to your do you achieve things to say you're done. You can't say, because of numerical reasons, you can't say 12,000 exactly. You have to say 12,000 plus or minus, and the tolerance here is 0.1 kilometer. So now we're ready to go over to the third tab. If I did everything right, big if, it should work. So let's give it a shot. Hit the blue run button. Okay, so let's take a look at it. It's always good to qualitatively look at your graph to see You can just eyeball it and see if it did what you wanted to most cases. All right. So we started here. We propagated to perigee, applied a maneuver, and went to apogee. But this is a little hard to look at because the burn segments aren't highlighted properly. So let's change the colors a little bit so we can kind of understand the picture a little bit better. Okay, Rizwan, what button do I hit to get the colors?
Oh, that's in the output tree. You're in the output tree. You need to.
Back to resources.
Yeah, there you go. Are you trying to change?
Mission and for propagate the maneuver.
Are you trying to change colors for each
Yes.
finite burn?
Yeah.
Oh, then yeah. Michael is right. Yeah. Mission tree. And then propagate for burn duration. That segment. It's okay. I got it. Oh, yeah, there you go. You click on that and then give it whichever color you want.
Okay. So let's pick a different color for the burn duration so we can pick it out. So you have to override the segment. Have you gone over this before?
Yeah,
Changing the color?
Yeah.
Okay.
But for this,
So it's very good when you're looking at the picture to put your segments different colors so you can line things up. So the burn's going to be in green. And then I think you have to rerun it to get the picture. You have to rerun it to get the picture, the color to change. So here, this is a lot easier to follow. So you start here. The red is you propagate to perigee. The green is the burn. And then this is just natural propagation to apogee. So just from the picture, it looks like it worked. And down here in the message window, you have took 13 iterations to converge, and the burn duration was 1,213 seconds.
What's that little red segment after the burn?
I think it's little remnants of the differential corrector progress. Right. So maybe it probably shouldn't. I'm guessing it shouldn't be there.
if you
if
you apply corrections and you
run it again, just as a natural.
yeah, then I think it's going to overwrite that final the teal color. It's going to make it red. We saw the same thing in the Mars deep learning targeting.
So do I have to run it again?
Yeah. See if it,
It's still there.
go ahead and do it.
So that's a little feature.
But you could change the prop to apogee color, right? That in that particular segment, right below the turn cluster off.
Yeah,
And you could make that some different color.
and it'll overwrite it.
Yeah. I'm pretty certain it will.
So let's make that a different color. Yeah.
So that teal color is actually that target color that it.
Is that a bad color you're saying?
Oh no, the teal color that you're seeing actually in the by
Yeah.
default is that the color that GMAT draws that gives it to that perturbed final solution. Still not doing it.
Yeah, it's still. I'll ask about that.
Yeah, it's
'Cause
actually it's happening on Mars deep learning targeting
Yeah.
also. Instead of drawing the final red
Yeah,
color, it's still drawing
Yeah.
that teal color.
I'm not sure why.
So solution.
It might be that I don't understand what it's doing, or maybe you needed something that we need to tweak. I'm not sure. I'll look into it. Okay, so now the picture looks okay. So let's go to the output and actually look at things to make sure it did what we want it to do. So actually, it's actually in the mission section. So let's open up the various command summaries for the various segments. So this says this is to propagate to perigee. So if it really is perigee, the true anomaly should be 0, and the mean anomaly should be 0, and it is. So you really are at perigee. So that worked. So this is the burn segment, and we ended up with 343 kilograms. And if we look at what we started with, it was 650 or something. 756. So we used about 412 kilograms of fuel. Let's confirm that we really did propagate to apogee. So the true anomaly should be 180. And it is, so that worked. And let's look at command summary here. We're still at apogee. Mean anomaly, true anomaly is 180. Did we achieve the radius of 12,000 that we wanted? Let's take a look. So that would be R. R mag, 12,000. Did we achieve it within 0.1 kilometer? Plus or minus 0.1 kilometer, we did. So this was a simple case. There's things that we could do to improve it. We started the burn at perigee, and then we let it go for 1,200 seconds. But we know that the best place to perform an apogee raising burn is really centered at perigee. So maybe we want to make half the burn before perigee and half afterwards. So the burn is kind of centered right along perigee. So there's various strategies you could do. You could, at the end of the burn, we could look at what the mean anomaly is. It's 25 degrees. We started at a mean anomaly of 0 when we finished at mean anomaly of 25. Well, maybe instead of starting at 0 degrees mean anomaly at perigee, we could have started at a mean anomaly of negative 12.5. Or maybe we could have propagated to perigee and then backtracked half of 1,213 seconds, 606 seconds, done that. Or if you really wanted, it depends on how much fuel you have and how much time you have, how finely you're going to slice this. If fuel is really an issue, you could, don't even use the targeter differential corrector, you could use the optimizer. And with the optimizer, you could vary the burn duration. You could have a constraint. Well, at apogee, the radius needs to be 12,000. And then when you have an optimizer, you have to say what you're going to optimize. And this, you could optimize, minimize, in this case, fuel use or burn duration. So this is, and what are you doing? You're going to do next more of a really high-powered Joel's going to do a really high-powered optimization case. Yeah. With all kinds of segments and yeah. So this is the kind of thing that you'll definitely have to do if you're actually going to fly a mission in operations. Yeah, Mike.
So, how come for the turn thruster off that ends the finite burn? How come there isn't a summary? In the summary report, how long the burn was, how much fuel it used?
There should be.
Okay.
We just haven't gotten around to.
Okay.
Yeah.
Right. So right now you have to kind of find that externally and
right.
that somehow.
But
it would be nice since that object is turned the maneuver off. Obviously, the maneuver's over. we should spit out some summary.
Yeah, so these reports should be, in another iteration, we'll make the report a little bit more user-friendly, yeah. Any other questions?
Does that mean there's no way to see how long the estimate burn or the burn duration?
Well, it comes up in the that summary down below in the little, that section right there. It tells you what the burn is, and you can output that burn duration variable to an external report. Kind of make your own report, but it's not something that's done.
Or you could say, in the script itself, you could say report during duration
right
to a script.
Right,
yeah, it comes in the message window too.
Right. It's a message window, but you could output it to an actual report if you wanted to.
Right. Yeah. So all the information is here. But Mike's just saying he's used to seeing other software where the report, everything you want to need is in one maneuver report. Yeah. So that's a.
With some maturation, it'll get there.
Yeah. All right.
Yeah, for impulsive burn, we have a relatively quick summary.
Right, that's what I'm saying. That's why I was surprised. There wasn't anything.
Yeah.
You couldn't find it.
Yeah, you have to go to an extra step.
Yeah.
Right.
Yeah.
So Joel's up next. He'll talk about the optimization.